So good day, everyone, and welcome to this doctoral ceremony. This ceremony is also streamed on YouTube. And my name is Einar Örn Sveinbjörnsson, and I'm the head of the Faculty of Physical Sciences here at the University of Iceland. And I will basically guide you through this dissertation procedure, you might say. And the doctoral candidate today is Aleksei Ivanov, and his PhD thesis is in the field of chemistry. And the thesis is entitled Calculations of Ground and Excited Electronic States Using Self-Interaction Corrected Density Functionals. And the academic supervisor of this work is Professor Hannes Jónsson, sitting here close to us. He is professor at the Faculty of Physical Sciences here at the university. Then, together with him on the PhD committee, we have Professor Egill Skúlason, also present there. He is professor at the Faculty of Industrial and Mechanical Engineering and Computer Science, also at the University of Iceland. And then we have Einar Örn Sveinbjörnsson, who is a research scientist at the Science Institute here at the University of Iceland. So that's the doctoral committee. Then we have two faculty opponents. We have one on site, that is Professor Andrei Manolescu from Reykjavik University. He's at the School of Technology, Department of Engineering at Reykjavik University. And then we have one faculty opponent online, and he is Thomas Olsen. He's associate professor at the Department of Physics at DTU, or Technical University of Denmark. And he will be with us on Zoom and also on the stream. So the procedure is roughly as follows. First, the candidate will present his thesis for some time, and after that, we will have the faculty opponents that will questioning or examine the thesis. And as far as I know, Thomas will start with the questioning, and then Andrei will take over, and then they will switch maybe a few times during that period. So after they have completed their questions, you are allowed to come with brief comments or questions to the candidate if you please. And but after that, we will basically close the session, and I will go and meet with Andrei and Thomas on a different Zoom link in another room, and then we will basically return in some rather short time with the verdict of the examination, basically. So that's approximately the procedure. So what we do is that we start with Alex's presentation. So go ahead, Alex, and I will sit there.
Thank you very much for the introduction. So my name is Aleksei Ivanov, and today I'm going to present my doctoral thesis, calculations of ground and excited electronic states using self-interaction corrected density functionals. I'd like to thank the Faculty of Physical Sciences for accepting my thesis for the defense and organizing this event. Now let me continue with the presentation. To begin with, I will introduce the subject of my study, and I will discuss shortcomings and challenges of mean field approaches. And then I will move to discussion of orbital optimization methods, which I developed during my PhD study for calculating the ground and excited states. And in the last part of my talk, I will show you the application of self-interaction corrected density functional calculations of electronic states in the Manganese Dimer. So my study was focused on a description of electronic systems from first principle calculations, and today we know that such electronic systems are described by a many-body wave function, which satisfies Schrödinger equation. And today we have numerical methods which allow us to approximate this wave function quite accurately. However, this method shows unfavorable scaling with the system size. They're too expensive to simulate large systems. And the common tool of choice to simulate the electronic systems is a mean field description. That is when each electron is described by a single orbital. There are two main mean field approaches. One is exact, and it's called Kohn-Sham density functional theory. So in this approach, one introduced a set of single particle orbitals which satisfy the Schrödinger equation, and the potential in this equation is chosen in such a way so as to reproduce the density of the true many-body system. And the approximations which we do in practice is that we need to construct an approximation to the exchange correlation functional from this equation. The other method, which is called Hartfox Theory, it's also a mean field method, and in this method we approximate the true many-body wave function with a slatted determinant. And what we do is that we find a minimum of a exponential value of the true many-body Hamiltonian among all slatted determinants. And the popular extension of these theories to calculate the excited states is a time-dependent density functional theory. And I should say this method provides a fairly good description of valence, electrons. However, it has its own shortcomings. So, for example, it has a problem with the Rydberg excitations. The electrons are not binded in the atoms. And then this method shows strong dependence on the exchange correlation functional, especially for long-range charge transfer excitations. And you can see example on this picture. The charge transfer excitation from ammonia to fluorine, and results of TD, time-dependent density functional calculations, are shown by this bar. So, and as you can see, for when we use the semi-local functionals, the time-dependent density functional theory basically predicts almost zero excitation energy. And then when we add more amount of the exact exchange into the calculation, the excitation energy increases. However, charge transfer excitations, they are very important in applications, for example, in photovoltaics applications. And one example of such system is molecular photosensitizers, like iron photosensitizers. And relevant charge transfer excitation here is a promotion of electron from a metal center to the ligands. And what we would like to do is that we would like to describe photoinduced dynamics of such complex. And for this, we need to develop a robust approach which would allow us to calculate electronic structure of this method, and also would provide us atomic forces in order to perform molecular dynamic simulations. And the cost of this method should not be too expensive. It should be comparable to the ground state DFT calculations. And as I said, Kohn-Sham DFT is in principle ground state theory. However, when the external potential is it describes the electrostatic interaction of nuclei with electrons, one can generalize Kohn-Sham DFT for excited state as well. And what we do in practice is that we start with the ground state orbitals, and then we promote an electron to the virtual state, which describes the excitation. And then for this excitation, we need to solve a set of Kohn-Sham equations. And approximation which we do is that we still need to use a exchange correlation functional approximation. We usually use a ground state functional. And then results of this procedure is that the excited state and the ground state, they are not orthogonal. And because of this, it's very difficult to perform calculations of such system, because as soon as you start optimizing the state, it can collapse back to the ground state. And therefore, we need to develop a robust algorithm which would allow us to perform robust calculations of such states. Apart from technical issues, there are also shortcomings of modern approaches in these mean field theories. For example, atomization energies can be described quite well in Kohn-Sham DFT, but Hartfox theory usually underbinds the molecule. And then Kohn-Sham DFT can describe quite well delocalized states, but struggle with the localized states, and the trend is opposite in Hartfox theory. And then orbital energies, for example, HOMO-LUMA gap is usually too small in Kohn-Sham DFT, and in Hartfox is too large. And magnetic systems are generally challenging for both theories because this system has delocalized electrons and localized electrons. And what people do now is that they try to come up with a so-called hybrid functional where they mix two theories, but now the amount of the exchange in this approach treated more often as an empirical parameter. However, the problems which I just described, they often can be traced to the self-interaction error, which is inevitably introduced in the classical Coulomb energy when we just use the total density as an input. If we rewrite the total density as a sum of orbital densities, we can see that in this sum, diagonal elements will describe interaction of the electron with itself, and this is artificial. So, and what we need to do in practice is that we need to construct exchange correlation functional in such a way so that it cancels this approximation, but it can never do this completely in practice. And Perdue and Zunga, they propose a procedure which estimates self-interaction error for each single orbital and then just subtracts this error from Kohn-Sham DFT functional. But the problem here is that this functional depends on each and every orbital density. So it's not unitary invariant functional. We cannot use the canonical orbitals as we choose in Kohn-Sham DFT, and this is why we need to develop another algorithm to find stationary points of this energy functional. And these issues formed the objective for my PhD project. So I had to develop a new optimization method which would allow us robust calculations of the ground and excited states using both Kohn-Sham DFT and orbital density dependent functionals. Then I needed to implement these methods in a state-of-the-art software. We used code called GPO, which uses a project augmented wave method. Then we would like to assess producing a self-interaction correction on challenging systems where regular Kohn-Sham DFT is known to fail. And then in the final part of my project, we wanted to apply Kohn-Sham DFT and self-interaction correction to the calculation of the excited state using methodology we developed. So in the first step of my project, I work on an orbital optimization method for ground state calculations. And in practical calculation, we always expand orbitals in terms of some basis functions, and the coefficients is new parameters. And what we need to do is that we need to minimize or optimize the energy with respect to these coefficients. However, the basis sets can be chosen in different ways, for example, like atomic orbitals or plane waves, or we can even represent the wave function in the real space on a grid. And now I will focus on atomic orbitals, and other basis sets will be discussed later. So how we find optimal coefficients which minimize the energy functional? So we use a unitary transformation, and we know that any coefficient can be obtained from another coefficient by applying some unitary transformation. And C here is just a reference orbitals, it's initial guess to our wave functions. And then because it's a unitary matrix, we know that we can make a parameterization of this matrix using skew Hermitian matrices. And the fact that this matrix is a linear space, we can consider energy as a function defined on a linear space. And this is why we can now apply unconstrained minimization algorithms in order to perform the minimization. So to do this, we had to calculate the gradients of energy. It can be done analytically. And then also we needed to construct the preconditioner, which is, can be obtained as an approximation to the Hessian of the energy. In order to calculate matrix exponential, we could use two methods, for example, scaling and squaring algorithms. This is a general method which can be applied to both Kohn-Sham DFT and orbital density dependent functionals. However, for Kohn-Sham DFT functionals, it was shown that actually this parameterization can be simplified, and this simplifies actual calculations. And because this is a gradient-based minimization, we use quasi-Newton algorithms, because it's known from numerical optimization theories that they are quite efficient. And here is the results of this method. We call it exponential transformation direct minimization, ETDM. So we calculate 148 molecules, and we could see that ETDM converges in all cases and shows similar performance to a standard self-consistent field algorithms, which are based on Pauli density mixing. And this method fails to converge in 5 cases. Then we also use exactly the same algorithm without modification for calculations of ionic solids, and again we see a similar performance between the two methods. It shows that this method can be applied to both molecules and solids without modification. And also we simulated a bit larger systems, like for example liquid water configuration consisting of up to 500 atoms, and we can see that this method can accelerate the convergence by a factor of 2 when we use a special parameterization of unitary matrix. And in general case, which the algorithm which we also apply to self-interaction correction, it still performs well and even a bit faster than standard SCF algorithms. And here is conclusion to the first part of my talk. So we develop a method which is more robust than a regular self-consistent field algorithm. It works well for a variety of systems without modification of parameters of the algorithm. It outperforms the SCF method up to by a factor of 2. And most importantly for my project is that this method can be directly applied to orbital density dependent functionals such as Perdue-Zunga self-interaction correction. In the second part of my project, I had to extend this method to the calculation of excited states. As I said before, we would like to calculate excited state by promoting an electron from a ground state orbital to the virtual state and then by solving the Kohn-Sham equations. However, one can also show that solution of these equations is equivalent to the finding stationary point of the energy with respect to orbitals. And in fact, excited state can always be described as a stationary point of this functional. And what we see in practice is that these stationary points which describe excited state, they're usually saddle points. So the problem is that the SCF method fails to converge quite often for excited states. And here is just one example. For example, charge transfer excitation in nitrobenzene is promotion of electron from nitro group to benzene group. And it is known, it was reported in the literature that self-consistent field algorithm shows erratic behavior. And this is just one example. And therefore, we need to develop a method which is robust. And we know that direct minimization works very well for ground state. This is why we decided to try to explore it for calculation of excited states. And here are 3 main modifications which we did. So first, we need to use a preconditioner which can estimate the direction of negative curvature. So, for example, if we promote an electron from ith orbital to j's with a higher energy, then this number will be negative. And it demonstrates that ijth orbital pair has to be rotated in such a way as to maximize the energy. Then it is better to use quasi-Newton algorithms which can build approximation to the Hessian which can have negative eigenvalues. And for this we used a symmetric rank 1 algorithm. And then we also had to use a maximum overlap method. So basically this method just occupies the orbitals according to our initial guess, and during the minimization it always tries to keep the symmetry of the state. And here is performance of this method. So we calculated 98 excited states, and we can see that SCF, as expected, fails to converge in quite a lot of cases. And then if we use direct optimization, we can see that, for example, when we use this LSR1 method, it converges all the time. And also it converges by a factor of 2 faster than SCF algorithm. Then we calculated curve crossings of potential energy curve, or potential energy surfaces of carbon monoxide, and we can see that this method also provides accurate estimation of the atomic forces in this region, while standard SCF algorithms, they struggle to describe this region. And we also did preliminary assessment of Perdue-Zunga self-interaction correction on double excitations of in the hydrogen, and we can see that when we apply full self-interaction correction to PBE, results becomes in a much better agreement with full CI calculations. And this is conclusion from part 2. So we extended ETDM method to the calculation of the excited states. We call it direct optimization MOM method. It provides better robustness and faster convergence. Also, it can describe difficult cases such as curve crossing and more generally conical intersections conical intersections. And also this method can be directly applied to orbital density dependent functionals such as Perjuzunga self-interaction correction. So in the third part of my project, I had to extend this method for the use other basis sets. And let me explain you now why we would like to use other basis sets. So for example, we want to calculate excitations in ammonia. So if we use a standard correlated consistent basis set, with, which is used in the LCO mode, you can see the wave function here, it's green. But then if we do calculations with a finite difference basis set, it's, the basis, or the wave function is quite different from LCO. And in order to get agreement between the two calculations, we really need to expand the LCO basis set and add extra set of diffuse functions so as to get an agreement between two different basis sets. However, now if we would like to calculate another excited state, 3pz excited state, you can see that this basis set, which we just used before, is not sufficient enough to describe the wave function. And then we need to expand further the basis set, add extra set of diffuse function, while finite difference method without modification can describe all the states. This is why we need to develop a method which would allow us to use more efficient basis sets in practice. And what is the problem here? The problem is that if we use exponential transformation, we need to calculate this matrix, which has dimensionality m times m, and m is the number of basis functions. Now, the number of basis functions in this basis sets can be quite large. For example, it can reach 1 million, and this is why it's extremely difficult to calculate this matrix exponential efficiently. And the other problem is that we use quasi-Newton algorithm to conversion of saddle points, and then we need to use a lot of memory. We need to store a lot of orbitals from previous steps in order to construct the Hessian approximation efficiently. And this is just not usable with a finite difference basis set, for example. And so we wanted to overcome this problem, and this is how we do this. So we introduce a set of orbitals in our calculations, but we choose number of orbitals here is much less than the number of basis functions. But number of virtual states, empty states, should be large enough in order to get the excited state. And then we can apply unitary transformation to some reference orbitals. It can be our initial guess. And then we consider energy as a function of both, of unitary matrices and reference orbitals. And what we do then, instead of finding the stationary point in a huge dimension space among all wave functions, we just do a double loop optimization. So first we find a stationary point among all the unitary matrices of small dimensionality, and in the outer loop then we perform a regular minimization with respect to wave functions. And this is a much simpler task. And we apply this method to the calculation of this charge transfer in nitrobenzene, and we can see the direct optimization method shown here by red dots converges nicely to the excited states, while other ACF-based algorithms, they show erratic behavior. Then we use this method to assess the Perjuzunga self-interaction corrected functionals on the excited state of valence and Rieberg excitations. So we can see when we apply self-interaction correction to a valence stand, unfortunately the error is increasing, but it doesn't increase that much by only 0.2 eV, and this is a small number as compared to the excitation itself. But for Rieberg state, we see an improvement. And what one can see is that, for example, scaling by half, it can be a good compromise to describe both states. Then we apply this method to the calculation of charge transfer excitation in iron photosensitizers. As I said, relevant excitation is from metal center to the ligand. And from the experiment, we know that maximum absorption peak correspond to 2.71 eV. And what is also known is that oscillation period in a metal center state is 278 femtosecond. So we applied a developed methodology to the calculation of the potential energy curves in the excited state along the metal ligand stretching normal coordinate. And the brightest state, which is shown here, has an excitation energy of 2.57 eV, which is in a good agreement with the experiment. And also we calculated the oscillation frequencies in this state, And we got, again, a good agreement with both experimental results and time-dependent density functional theory calculations. But furthermore, we were able to calculate another metal-to-ligand charge transfer states, which can be important in a simulation of ultra-fast dynamics. And we just show that our algorithm is good and robust and can access the states, and we expect that it will be used in a simulation of dynamics of the states in the future works. And this is conclusion from part 3. So we develop a new method for calculating excited states within plane waves and finite different basis sets. This method is robust, and I think we can now perform the dynamics of excited states. And we also assess producing a self-interaction correction and on both valence and Rydberg states, and seems that half-seq provides a reasonable compromise for 2. And this is in agreement with the ground state calculation, where we know that we need a half-seq in order to describe accurately atomization energies and also band gaps. And now I would like to continue with the last part of my talk. So manganese dimer is a very small but extremely difficult molecule for both wave function approaches and Konsham DFT. What we know from experiment is that it has a large bond length, 3.4 angstrom, and the binding energy is small, minus 0.13 eV. And the wave function method predicts similar bond energy. However, they differ in estimation of the bond length. And now if we perform calculation of the system with one of the most popular functionals, such as PBE, what we see is that the ground state is actually much lower in energy by 0.8 eV, and the bond length is very short. So we try to analyze the reason for this, and we estimated the self-interaction error for different orbitals, like s orbitals, p orbitals, d orbitals. And what we can see is that self-interaction error in s orbitals is quite small, but it's very large in d states, and it is negative. Now, if we have a small band, like energy separation between s and d electrons, then the semi-local functional will prefer the state which has more d electrons in it, because it has a large negative contribution in the energy. Then we calculated molecular orbital diagram for this state, and indeed we can see that PBE predicts that HOMA state will be linear combination of d orbitals, and the unoccupied state will be just sigma star for s state. Now, if we apply self-interaction correction to this state, what we can see is that energy of d states, P3D states, becomes higher in energy because we remove the self-interaction correction, which is very large for the states, and now sigma star for S states become lower in energy, and what we get the right symmetry of the state, which is observed in the experiment. Now, if we perform full calculations of potential energy surfaces, we can see that this curve, which was a ground state and PBE functional, becomes actually excited state with self-interaction correction, and the results for other states we calculate in a good agreement with the experiment and the wave function formalism. So, and this is conclusion from part 4. So, Konsham DFT calculations with semi-local functionals have difficulties to describe the manganese dimer. And if we apply self-interaction correction, we can accurately describe the state, and we think that the main reason is really self-interaction correction and not a strong correlations, which people often refer when semi-local functional fails. On this, I would like to summarize the results of my dissertation. So we develop a fully variational method which allows us to calculate ground and excited states using Konsham DFT and producing a self-interaction corrected energy functionals. This method is robust and it provides atomic forces. This is why we can use it in a simulation of molecular dynamics of excited states. Then we also calculated electronic states of manganese dimer and showed that it can accurately describe such system where semi-local functionals and fails. The most important thing is that now we have implemented these methods, and we finally can focus on the development of better approaches than producing the self-interaction correction, better forms orbital density dependent functionals, and this is a very exciting and new area which I would like to do in the future. Then we showed that this method, which we developed, it demonstrates superior performance as compared to a CF algorithm, and this is why we think that it will be used in a simulation of the excited states. And finally, we implemented this algorithm in a GPO software, which makes use of project augmented wave method, and it can be used to calculate now excited state in condensed matter systems. On this, I would like to finish my talk, and I would like to thank you for your attention.
So thank you very much, Aleksei, for a nice presentation. Now the examination begins, and we will first like to ask Thomas Olsen to start the questioning. We might have to do something with the computer to see him, I guess.
Mm-hmm.
You see there somewhere?
Mm-hmm.
Are we on Zoom now?
Yeah, I think this is Zoom.
Okay. Yeah, it is. But is Thomas there? Don't see him. Okay, he's okay there. Okay, there he is. Okay. Houston, we have a problem.
Oh, there he
is. Okay. I was maybe just watching the stream. Now it's there.
Mm-hmm.
Yes, sorry, I had to switch off Zoom because I couldn't. Well, there was double sound from YouTube and Zoom, but now.
Now you're with us. So. Yeah. Okay.
Now you do, all the time.
please go ahead, Thomas.
Well, first of all, thank you very much for a nice and lucid presentation. I think you did a good job in presenting everything in a very clear and pedagogical way. I also enjoyed reading your thesis very much. It's, I think it's a very nice work. You've done some very technical stuff about the implementation and algorithms, and still managed to also to apply it to some very relevant systems where important effects and really unravel this need to include self-interaction corrections to various systems where known local and semi-local functionals fails. So I think this was really nice.
Thank you.
Of course, I also have some questions. And now my first question is, well, I think I have a few rather general questions and also some technical ones. So the very first figure you showed, or I think maybe one of the first ones, was a table where you showed what DFT and what Hartfox can and cannot do.
Yeah.
And there was one cross in that in the DFT table that I didn't like too much.
One second.
If you can find it.
Yes. Mm-hmm. So is it this slide?
Huh?
So this is a slide.
Yes, this is one. So can you guess which one I disagree on?
Sorry, could you repeat again?
Can you guess which cross I disagree on the DFT side?
Oh, sorry, I cannot hear properly.
Can you guess which cross he disagrees on?
Ah, which cross you disagree on? Oh, okay. I'm not sure. I don't know.
What you're saying is that DFT cannot do localized states. It cannot do orbital energies, and it cannot do magnetic systems.
Mm-hmm.
But the last one, I'm not sure I agree on.
On the last one, on magnetic systems.
The last one.
Yeah, so...
Why do you say that Colchamp DFT is not good at magnetism?
So, okay, so the problem with magnetic systems is really d electrons, right? So, and they are very localized. And actually, if you use semi-local functionals, they usually fails to describe such systems, for example, as a manganese dimer, or we also, in our group, we simulated iron clusters, and where the length of magnetic moment from Quantum DFT was extremely small. And what people do, actually, sometimes they do DFT plus U calculations, but I didn't include DFT plus U as a Quantum DFT method, because this method is just trying to mimic the self-interaction correction. And yeah.
Okay, but if you do an oxygen molecule, for example, that's spin polarized.
If you do spin polarized, so if you do symmetry breaking calculations, so.
Yeah, sure. I mean, I suppose this is also what you do, right? When you calculate the manganese dimer.
Sorry, it's very difficult to hear from the speakers.
Okay, I suppose you're also doing broken spin symmetry when you're doing spin
Yeah,
polarized.
if I do a broken spin symmetry, yeah, so for example is like this last example of a manganese dimer. It's magnetic system, right? It has a ferromagnetic state, and it has antiferromagnetic state. And of course, we always use a spin-broken DFT. So, and what we can see is that DFT just failed to describe the state. So it just predicts wrong ground state. Of course, it might be one extreme example of molecule, but we saw similar behavior in clusters. And unless you do some self-interaction correction, sometimes, yeah, if you do like DFT plus U, or you can try to fit a hybrid to the system, you will be able to describe it. But commonly used approximations, we also tried MetaGJ functionals, like recently developed scan functionals, and they also fail to describe the correct ground state in this system. So I don't think that
I don't think this system is representative of magnetic systems in general.
Yeah, so yeah, this is as one example, but then, as I said, we simulated iron clusters, bigger systems, and it also has the problem there. Maybe another example which is more interesting is iron oxides, right? It's I think it's magnetic system, and we know that if we use semi-local functionals, you will get just a zero gap there, right? And I think the problem is really d electrons there, localized electrons. And you need to apply, again, U there, like, which mimics self-interaction correction. So yeah, transition metal monoxides is a good example where semi-local functional fails, I think.
But they still, I mean, semi-local functionals still give you an antiferromagnetic ground state for nickel oxide, manganese oxide, iron oxide. It might be that the gap is zero, but that's a different story. I mean, that's no one said that the Kohn-Sham gap is supposed to represent the true quasi-particle gap.
Mm-hmm. Yeah. So yeah.
I mean, if you calculate bulk iron, bulk nickel, bulk cobalt, bulk chromium, you get the correct ground state with LDA.
Yeah, yeah. This is systems indeed, and this is the reason is because it's metallic system, and it's really electrons there are quite delocalized.
But if you do nickel oxide, manganese oxides, you get the correct ground state with LDA. It's antiferromagnetic. Yeah,
but but I don't think you get the correct lattice structure, actually. There is a paper recently published by the group of Purdue where they studied different structures of transition metal oxides, and they show that actually even if you get antiferromagnetic ground state, you not necessarily get the correct lattice structure. So you need to apply like U correction, and then they also argued that you need to apply van der Waals correction to the system. So I think at least I can say that magnetic systems are very controversial, and people develop a lot of different methods to describe that. So I think we still have this problem of description of magnetic systems with commonly used functionals.
Yeah, maybe.
Yeah.
I mean, they're certainly more tricky than non-magnetic systems, but I still think you can get a long way with semi-local functionals. Mm-hmm. Okay, let's leave it. I mean, it's but surely there are examples where it fails. That's for sure.
Yeah.
Yeah, so maybe just a general question, is this implementation, is it part of the master branch in GPOR as it is it still a development branch?
So actually, LCO code, I sent this merge request a long time ago. I don't know, maybe you can see when it was sent. It was maybe sent a year ago or something. And then we recently, Jens commented that if we need help, he updated it to the most recent version of GPO. But then also we have our own branch, TheoChem, GPO, and the code is there, it's available, and everyone can use it. And we would like now to send a merge request to the main GPO branch in the coming weeks.
Okay.
Yeah, but I know that a few people actually requested this code from us, and we shared the link, and I think, yeah, it's available.
Yeah. Because I think, at least, I mean, if we start with just the ground state calculation, it looks like it's, I mean, the direct minimization method, it seems to outperform the standard SCF method.
Yeah.
So really, I mean, the examples you showed, at least, it's better, right? So why not just use it all the time?
Why not to use
the direct minimization all the time? Why not make it default?
Yeah, I agree. It would be very nice to make it as a default. I'm only for it. I will be very happy if it will be a default method, of course.
Yeah. I mean, it would be nice because I'm also looking at a lot of magnetic systems, and there I mean, there's often convergence problems which are difficult to get around. I mean, it's not always clear what to do, and it seems like the method is much more robust, at least, and that would be really nice if we get a robust method that just works all the time. But and it seems to do. I don't know. Do you have examples where it fails that you perhaps didn't show, or does it just always converge?
Do you have examples
where it fails?
Do you have examples when it fails?
Yeah, I don't actually have examples when it fails. So actually our main motivation was, at least with LCO, I'm pretty sure it should perform really well, because we implemented the method which is proven by mathematician converges all the time. So we performed a special line search algorithm, and I'm sure it should be very robust. Maybe for metallic systems, I saw a few examples when it converges, but it doesn't converge, for example, to the lowest energy state, and then you need to do some tricks there. But it should always converge to some stationary points. At least if you give it maybe more iterations, I don't know, like 300 iterations, you will see sign of convergence at least always. Yeah.
Okay. I mean, you want to be sure you found the ground state at least, right? That's an important point.
You should be sure that it
That you found the state of lowest energy.
Yes. So this is actually an open problem. So there are a few methods which allows to do that. So how we can ensure that we converge to at least to the local minima? So as I said, for example, in LCO method, we make parameterization of the exponential matrix, right? Using these Q-Hermitian matrices. So and what one can do in principle, so we calculate the gradient, but what we can do, we can also calculate second order derivative, right?
Yeah.
And then first derivative will be 0, and then second order derivative, if we calculate it and find the lowest few eigenvalues of the Hessian, it will demonstrate at least that if it's a local minima or a saddle point. So we have actually a function there which does it numerically, but right now is not very efficient because it just calculates the whole Hessian and find all eigenvalues. And in the future, we are planning to add something like Davidson or Lanch's algorithm, which will just calculate one or two first eigenvalues and check if it's a local minima or not. If it's not local minima, then you can, because you already know Hessian, you can estimate the direction of the negative curvature and just to rotate your orbitals along this curvature. And then your energy will be decreasing. So this is still a work in progress. Yeah.
Okay. But it seems like an important point, but also a point that can be solved.
Yeah, this is an important point, and in fact we use this for excited states. For saddle points, when we converge, we try to identify the order of the saddle point and look at the Hessian and how many negative eigenvalues it has for excited states.
Yeah, so that was perhaps also my next question. And when you do the excited state calculations, how do you know actually that, I mean, you target a particular excited state?
Yeah, so
you do this by this maximal overlap.
So
couldn't you just, I mean, if you don't do the maximal overlap method, can you just find saddle points and then order them and say, okay, this is a range. We don't know what they correspond to, but this is a set of excited states.
Mm-hmm.
Can you do that?
Yeah, so basically, actually, in this example, for example, when we calculated 89 excited states molecules, it converges, LSR1 converges quite fast. And actually, it's never used over maximum overlap during the iteration because the optimization was quite robust, and it converges to the saddle point, which is the nearest to our initial guess. But then we saw that several excited states, so if I aim at one specific excited state, in fact, there can be several saddle points which have the same symmetry as a saddle point, as an excited state we want to calculate. And this is, I would say, this is maybe drawback of the method, that there are so many saddle points, and sometimes it's difficult to understand which is the most relevant and describe the desired excitation. So, but yeah, maximum overlap method is really like a backup method. As soon as you miss the saddle point and start converging to the ground state, maximum overlap can identify it and promote electron back to the excited state, and you continue again saddle point optimization.
Right.
Yeah.
But can you find spurious saddle points that does not correspond to physically excited states?
Yes.
You risk doing that?
Yes, in fact, actually, in our group, we work on that, and there are examples where people did calculations of the excited state before, and they reported that that results are horrible, not physical. But in fact, the reason was for that they just there is another saddle point, which has more physical meaning. So yes, it is possible to converge to a saddle point which physically doesn't correspond to the excitation we really want. I don't know if I answered your question.
Yeah, but what is it then? Is it the problem with the functional?
Yeah, so this is a good question. It can be the problem with the functional. It can be, so in that case, if I remember correctly, the problem actually was that people use spin-restricted calculation. You have spin density up, spin density down, and you restrict like this calculation. And you can converge to a saddle point, which represent excited state, and it seems like it's just doesn't have right physics. But then if you break the symmetry of the functional and use spin polarized calculations, introduce like in some sense static correlations by breaking the spin symmetry, then the saddle points becomes good. It has a more physical sense. So I think maybe the problem is a really static correlation problem for excited state.
Okay.
Yeah. So that, yeah, maybe in some cases, yeah, single set determinant is not good enough. Yeah.
So another question I have, I mean, so you compare these direct optimization maximum overlap method with traditional self-consistent fields. And now here you have an example where this is compared with self-consistent field and maximum overlap, right, in this slide here.
Yes. So
because, I mean, you started by stating some very erratic behavior in a molecule where you see that the energy fluctuates up and down.
Yeah.
And I think that, I mean, the problem there, I think, is that you do not enforce a maximum overlap. So if you just enforce occupation numbers to be occupied, then you can, I mean, you flip around occupation numbers and the iterations.
Mm-hmm. So you mean this problem?
Yeah.
So actually, it's confusing. I should have wrote SCF mom.
So this is maximum overlap.
Yes, this is with maximum overlap. And actually the problem here is that because we excite electron from this orbital to here, the energy separation between these orbitals and nearest orbitals is very small. It's like 0.5 V or something. And then when you do diagonalization, it just constantly occupies different orbitals, and this is why it starts oscillate. So you need to apply really some smearing.
Okay, so, but maybe then I don't understand what you mean by maximum overlap. Because I mean, I thought that you meant exactly that you specify which orbital you want to depopulate and which orbital you want to populate. Because if you do that, you cannot, I mean, they will not switch around. They will stay where they are. I mean, you're sure that it's the right orbital that you leave empty all the time.
Yeah, this is a good question. So you're saying that maximum overlap should always occupy the correct state, and it should not oscillate. Yeah, I see your point. Let me remember, how was it? So,
are you sure this is with maximum overlap? I mean, what do you mean by, I mean, because what I think about maximum overlap, you do it in each step of the iteration cycle. It's not an initial guess, it's in each step.
Yeah, maximum overlap is applied on each step. Yeah.
And then that can't happen.
Yeah, it should, this is what we also expected, and that it should converge. But for some reason, it doesn't converge still. But I remember we analyzed it, and somehow we came to the conclusion that the problem was really closely lying orbitals, like that occupied and unoccupied orbitals lie very close. I think it might be similar to the charge slashing problem in the ground, similar to the ground state DFT, that if you just mix orbitals a bit, then your potential changes a lot and you have a large jump in the energy. So,
okay.
So this can be potentially the problem. Yeah. But also the maximum overlap method we used, so you need to set like some initial guess, right? In this method, and use this initial guess as a reference. And I just wonder if during the optimization orbitals changed quite a bit, so that they are quite far from this initial guess, and that it starts occupying some random states. You see what I mean?
Yes, but then there should be other states that have larger overlap with the initial state you specified. And that's also unlikely.
Yeah, so there can be, yes.
I mean, the reason I asked you, I don't know if you know, but I mean, I was the one who, during my PhD, implemented the maximum overlap methods for delta SCF in GPOL.
Yes.
And we saw this problem exactly, that if you just specify occupation numbers, I mean, you're bound to fail due to this problem. But if you're careful about selecting which orbitals, which kind of symmetry, or which kind of orbitals you want to have occupied, then it works most of the time. Maybe not always. I mean, we didn't do that many calculations. So, but I mean, your method seems more efficient in any case. So
thank you.
I think it's very nice. Another question. Well, I want to ask you a bit about the spin purification you're doing. You had a formula for the spin purification.
Yes, I did have some. Sorry, didn't I show here?
No, I don't think you showed it.
No, okay.
But you know which one I'm talking about,
Yeah,
right?
so it's, yeah, I do.
So where does this formula come from?
So basically, if you describe open shell singlet, so you have okay, electrons will spin up, electrons will spin down, and they have different spatial symmetries in different spin states. So the correct wave function should be like some linear combination of that, right? And one can show that this state is a mixed state. It's just the sum of the per singlet state and per triplet state. Now, if you take this wave function, plug into the expression for the energy, so you just get that energy of this mixed state is just half of the energy of per singlet and per triplet state. And then you just can express singlet state. And the thing that we can exactly, not exactly, we can accurately describe triplet state because it requires one single set determinant. So we calculate triplet state, then mixed spin state, and then we can approximate, yeah, the...
That's right, yes, okay. Yeah, I was just curious if you, I mean, you don't derive it, but I was just curious, but it sounds like you know how to derive it.
Thank you. Yeah.
Okay. So how accurate is it actually?
So it's...
the triplets, as you say, you can describe, well, exactly up to the accuracy of the functional you're using, right? But the singlets you cannot. So you use this mixed state and use that to get the singlet energy. And I'm just, so
how accurate this equation
approach itself?
So this state is actually, this method, at least I can say that it's much more accurate than just using mixed spin determinant.
I mean, the mixed state is as much a triplet as it is a singlet. I mean, it's equally triplet and singlet, right?
Yeah. So yeah.
So that's not a good state to use.
No.
I mean, you need to do something else, and we do this approximation, but it's just not clear how good an approximation that is.
So okay, what we know from practice that it's it gives how to say it? I don't have a slide here, but as far as I remember, the error is still larger than in the triplet states.
Yeah.
So if I remember, the energy error bar in the triplet states, mean absolute error was like 0.2, 0.3 eV with PBE, and then if you use a spin purified equation for singlets, I think the error was around 0.5 eV, something like that. So the error in singlet state is still larger than in a triplet state.
Yeah. Okay.
Yeah.
Okay.
Yeah.
And how do you actually do it for the Manganese Dimer? That was a bit puzzling to me because you don't have a triplet, you have I don't know what's it called. That's 11 spin states.
For
Manganese Dimer.
So for Manganese Dimer, okay, so how would do that? So this is ferromagnetic state. You don't need actually to apply any spin purification formula there, right? And then we have
What is the spin purification formula for that? Because there now you don't have a triplet.
Yeah, so I'm saying that, there is no spin purification formula for that.
But there's no, okay.
Yeah, this is just a high spin state.
But how do you get the singlet energy then?
So antiferromagnetic singlet, so we just use spin broken DFT. We don't apply spin purification correction here.
But that will give you the mixed state, right?
But it will be a mixed state. One second. Will it be a mixed state? The thing that special orbitals in a spin up and spin down, in this case, they very similar. So this problem doesn't arise here. We don't have this problem here because it's a simple molecule, like a diatomic molecule, and this singlet state is actually antiferromagnetic, right? So you have one electrons localized on one atom, the other electrons localized on the second atom, and spatial orbitals, they very similar. So it's not the same as to describe open shell singlet where you really have a just spin up orbitals so different from spin down. Do you see what I mean?
No, well, I see what you mean, but I think I disagree. I think it is the same. I mean, the problem might not be as severe, but I think it's the same. I mean, what about an oxygen molecule? I mean, there you have a singlet state, right? There you have singlet states.
In what molecule?
I mean, if you...
yeah, O2, yeah.
No, so do you believe that if you observe this, in nature, do you think that the spin-up density is either on one atom or the other? Or do you think that both atoms have zero magnetic moments?
So in this case, in manganese, each atom has a final magnetic moment. Hello?
I don't think so. It's a singlet. It's not an antiferromagnetic state. That would be my understanding at least.
So basically, I can tell you that actually this will be antiferromagnetic state shown by red, but then you can have a singlet which is ferromagnetic state.
Yeah.
So you can have both, and this red one is for sure antiferromagnetic state. We just specify the local magnetic moment in the beginning of the calculation, and then in the end we just see that you have spin densities are different. So this is for sure antiferromagnetic state, and this is ferromagnetic.
Sure, so, I don't disagree, but I'm just saying that the real manganese dimer is not antiferromagnetic.
Real manganese dimer?
Singlet.
Sorry?
I realize what you're simulating here, but you're not simulating a singlet. You're simulating an antiferromagnetic configuration, which is something different.
He's saying that manganese dimer is not antiferromagnetic.
In a reality.
Reality.
So basically, but this is a trick with Konsham DFT. No?
Is that statement correct?
Yes. In the experiment, they know that and wave function formulations give antiferromagnetic state as a ground state. So they calculate spin multiplicity in this sense. Of course, I think if you do wave function formulation and have all determinants, spin density up should be the same as spin density down. But because we use a single flat determinant, we break the symmetry and we can describe only just one spin configuration. But multiplicity, I think, should be the same, spin multiplicity.
Okay, but I'm just saying that you're simulating a mixed state. You're not simulating a singlet.
Mm-hmm.
That's
okay.
That's what I would say here.
Okay. So
maybe.
Okay. Yeah.
What's the connection?
Yeah.
I don't know. I might also be wrong. That would just be my feeling about it.
Mm-hmm.
Okay, maybe I should. I don't know. How much time do I have? I can keep going, but I don't know. Maybe Andrei would also like to ask something.
Sorry.
So I was just asking how much time I have. Because I keep going, but I can also let Andrei into the game, or
Basically, there's no time limitation in a way, but you maybe want to let Andrei discuss something and then come back. It's up to you.
Thank you very much for these preliminary questions.
Right, so maybe Andrei will take over a bit.
So it's my turn to thank you for the presentation. I have to say I belong to a different community. I'm not in chemistry or theoretical chemistry. I'm a solid-state physicist. And I use DFT, but I have the feeling that we are talking slightly sometimes about different interpretations, but still I believe there is a basic understanding that is common. So first, can you go to the, I think, slide number 2? Or next?
3.
One more. Okay, here. So you introduce a density functional theory through the Kohn-Sham equations. And then that's what I read here. And I remember. Of course, you may have, you may want it to have a brief introduction, but I want to check that whether we think the same way or differently. Whereas the second part of the slide says that Hartfox theory has to do with minimization of an energy. So, at least to my knowledge, these are different formulations. So, do you agree with me that it's a bit of comparison of pears and apples?
Yeah, so, yeah, this is two different theories. Like, so, okay, in
Two different theories of what?
Of approaching the same problem.
Okay, so each approximation, density functional theory is still an approximation in the practice. Practice has two forms.
Yes.
And then you choose form B for theory 1 and form A for theory 2, so to speak, Do we agree?
Yeah, for, you mean...
so, okay, can you clarify this?
Yeah. So, okay, so basically, okay, Kohn-Sham density functional theory, it's a practical way to do the calculations. So there is a more basic theory, which is just Hohenberg-Kohn density functional theory, and it just says that the total energy is just the energy of the density. Yes, it's not shown here. And Kohn-Sham DFT just says, okay, how to do this in practice in an efficient way, how to do these calculations just by introducing the single set determinant.
But isn't that true for a Hartree-Fock?
Actually, in Hartree-Fock, it's different because what we do in Hartree-Fock, so okay, in the Kohn-Sham DFT, what we do, we have a many-body system, true many-body system, and then we map it in such a way to the non-interacting system, such that density of this in a non-interacting system is the same as a true many-body problem, like in a Schrödinger, which follows from Schrödinger solution. Hartree-Fock doesn't do this. It doesn't try to find wave function which has the same density as a true many-body function. So Hartree-Fock is just says, I would like to do minimization as an, I would like just to solve Schrödinger equation, but just using single-theta determinant as an approximation. Okay. So yeah, both theories use single-theta determinants, but they really like attack the problem from completely two different.
But do you agree with me that if you perform the minimization, considering big phi's as later determinant, you end up with an equation that is a Schrödinger equation where you have what you have up, except what?
So except the exchange correlation potential.
No, except the small c.
Yeah, so
you will have Vx, not Vx.
Yes, there won't be correlations. Exactly. So I agree with that. Yes.
Yeah. Now, Kohn-Sham equations look like
Hartree-Fock
plus a correction, which is a correlation energy.
Yes.
But they are derived, as you say,
Yeah.
based on the idea that the energy is a density
Yeah.
functional
Yeah.
of the density.
Yes. Yes.
Which energy?
The ground state energy.
Aha.
Yes.
So now we go to the next question.
Yes.
Can you
Yeah.
explain me how do you, okay. because-
Motivation for the excited state.
Exactly, because this is a fundamental aspect
Yeah.
and it is actually based on a lot of empirical observations that still you
yes.
can, while in the Hartfox theory you have no fundamental restriction
Yeah,
of
I agree.
calculating the excited states. But your approximation of the Coulomb effects may be wrong. In particular, I have this experience in some systems is coming up, in other systems maybe not, that the exchange interaction is too strong, artificially strong,
Yeah.
and if you include correlations, you may combine with and you reduce those effects.
Yeah.
Then, it's a whole controversy and the whole, took a long time until people realized that they can still describe excited states. But these need to be a little bit clarified, so maybe in the, do I remember correctly? Slide 18. Can you explain
Okay.
to me one more time?
So actually, I was expecting such questions,
Yeah, yeah.
general questions,
Yeah.
and I prepared an extra slide for in this case.
Because you also mentioned in the previous answers, okay, you can have excited states that simply show up
Yeah.
as spurious,
Yes,
numerical.
yes.
Yeah. So
Yeah.
then,
Yeah, this is not good. I agree. So,
yeah.
okay, so what is maybe just to begin with general idea. So as you said, with Hartfox, in principle, we don't have this problem to calculate excited state, right?
No.
So what we would like to do, we would like to do some variational principle calculations. And of course, for Kansham DFT, yes, we need to, so here we need to be a bit more pragmatic, because it is indeed known that for Kansham DFT, just for DFT, you cannot approximate energy as a function of density only for excited states, right?
Because-
However,
Yeah.
we are working with a very particular systems. So we always know what is external potential. And then, for example, if we can calculate on this slide, I show you the ground state density, and this is excited state density of the dihydrogen. Okay? So now what we can see from this plot is that these cusps of the density, they define the position of atoms.
So are you saying that in the excited state, the density becomes more narrow?
This is what I obtained from calculations.
Not excluded, but I'm a bit surprised. I thought
That
the
is,
system is going
yeah,
to-
so,
Okay,
yeah,
fine.
okay. But what we can see is that the ground and excited state has these cusps, and these cusps defines position of atoms, right? They're exactly at the position of atoms. And then there is a theorem from quantum mechanics, it's described in these papers, which says that if you take this density and take a derivative of this density at this position, you can define a nuclear charge. And then if we work with an external potential, which is a Coulombic, then from this density, both excited or ground state, we can strictly define the external potential. So the density in Coulombic systems, whether it's excited state or whether it's ground state, it defines the external potential. And then what can also be shown that this density, in this asymptotic region of the density, depends on the ionization potential and depends on its energy of the excited state. And just by using this equation, we can show that excited state energy of the excited state can be approximated as a function of density, but only if the potential is Coulombic. So, so there is no general theorem which says that excited state functional is a function of density only. This is not true, but we need to be a bit pragmatic, and we know that we work with very specific problems in chemistry, like with Coulombic systems. And for Coulombic systems, one can argue that you can still formulate the function of density. So, and then, yes, the question is, of course, how you then approximate this functional, and this is open question. I agree that it's not very strict, but the available approximations are now is a functional from the ground state. We just use the same form, mathematical form for excited state. And yeah, I agree that it's not very rigorous, and a lot more work needs to be done in this direction.
But you had a slide when you showed the Konsham equations and how you built your excited states, because naively speaking, what am I going to do? Like I do in Hartfox, I'm going to take the Konsham equations. This is a matrix equations. In the end, I'm going to get a spectrum, and I'm going to take a first state, and that's excited state. That's exactly back to the origin of the problem. So how are you selecting the combinations or which, and of course, that's basically your work, but can you summarize it for me, like a solid state physicist? Because I want to treat excited states, and I want to know whether your method is, by the way, or maybe after that, what are the regular software doing? Because when I calculate with, for example, I have some experience with Siesta, I have Quantum Espresso, VAS, they do band gap, and they give you the band gap in, but the band gap is an excited energy problem. And they say, in titanium dioxide, you have this. You use another functional, you have this.
So, yes, it's a good question. So, so how we calculate an excited state? So we first do the ground state calculations, and then we have, for example, orbital energies of the occupied orbitals. Like, for example, the highest occupied orbitals will be valence band, and then there are empty states. In solid state, it will be conjunction, for example, band, or some levels. So what we do, we just basically, just in the program, we change the occupation numbers. We say, remove electron from this band, from valence band, and put it into the empty level. And then what we do, we try to relax then the system, giving that we occupy this specific set of orbitals. And then in this case, this difference between the orbital we occupied and the HOMA, it will represent the excitation gap.
Yeah, but it is still based on a calculation which assumes it's a many-body system.
Yes.
So there you need a Coulomb interaction, and you need an exchange correlation potential.
And then what we do, we just use standard functionals, like PBE, for example, or usually we try to use semi-local functionals. Because they actually, if you have an okay density, they actually can provide quite good estimation of the total energy. They can give a bad description of the band gaps, but the total energy can still be okay.
But my understanding is your method depends on the external potential. Are you saying that your method, you develop your method for molecules?
Yes.
Am I right?
Yes.
And how about?
How about extended systems? This is, here I need to be fair that there is no right now strict theory behind that. Why would it work for extended systems? Because the potential doesn't decrease, right, in the infinity. But again, we approach this problem from very programmatic, because we need some inexpensive method to calculate these excitations, and especially in solid states. And this is calculations we want to do. I think if we develop algorithm and method which will allow us to do such calculations, and we will get a good results, then someone who has a more interest in the theory can back it up. So I think even though we don't have a strict theory for this, we shouldn't stop. We still should develop this method and show that they work. And if they give a good approach, give results in practice, I'm sure the theory sooner or later will be justified.
And how do you verify your results? Because sometimes you may have experimental results.
Yes.
As you said, there are artificial excited states. How do you exclude them? What is the comparison? Experimental, right?
So yeah, experimental, or people can use wave function approaches to try to solve Schrödinger equation.
You mean?
For excited states, for small molecules.
Okay. So
only for small molecules. They cannot do big systems.
that was my next question.
Yes.
Are situations where more accurate calculations are possible, like exact diagonalization? And
Yes.
then you can see
Yes,
whether you match?
possible. And usually we use this as a reference. Because
Have you done that with your method? Is it your method verified against?
So-
or maybe I missed the examples.
yeah, so for example here, we compare excitation energies in small molecules like a water molecule and carbon monoxide molecule. It's small molecules. And then it just was published actually recently. It's where people perform high-level wave function calculations of these systems just to create a database so that we can compare approximate method.
But this is a small molecule, right?
Yes.
I mean, I suppose these are well-known results. So every theory that
Yes.
has to do with the excited states wants to
Yes.
check, to be checked.
Yeah.
So I suppose all theories that do excited
Yeah.
states verify this case. Am I right?
So yeah,
Because if this is a simple case, water molecule, so if you don't
Yeah,
match
if-
that,
yeah.
you don't publish.
exactly. Yeah. So if we use it as a reference, and we always try to
So
compare
do you
it.
have a more
with-
complex situation
Yes.
that you can,
So to compare to, this is actually difficult. Yes, but for solid states, if we would like to calculate excitations there, you can use, I think, GW method. I'm not familiar with that very much, but as far as I know, there are some many-body techniques which allows calculation of the excited states. And maybe, but one need to look at this very carefully. Maybe we can take this sometimes as a reference. So, but usually, if it's solid state, yes, usually we just check it against experiment. Yeah.
or if you can, exact.
Yeah, or if we can, exact calculations when available. But the way we validate that we calculated correct state, right now is just we visualize orbitals, see the symmetry of the state, and if it agrees well with what we expect, then we accept it as a solution to the problem. Yes.
And when you talk about the generalized Kohn-Sham theorem, can you explain to me what is generalized?
So,
What do you, what particular aspect, what do you generalize?
so in these equations, in a Kohn-Sham DFT, we assume that the functional is a function of density, and then we minimize with respect to density. And then what happens is that this potential is just multiplicative. It's local, so it's just like if you use LDA or PBE, it will be local.
Then it becomes local, but
Yes.
fundamentally, okay, practically
Yeah,
it's probably,
yeah.
but not necessarily.
But in generalized Kohn-Sham, what people try to do is that they try to verify hybrid functionals, like exact exchange. So in a regular Kohn-Sham DFT, we map system of interacting electrons to the system of non-interacting electrons, right? In a regular Kohn-Sham DFT. But in a generalized Kohn-Sham DFT, we say, okay, let's map it to a system of partially interacted electrons. So by introducing Coulomb interaction a bit, in this, and still even we'll use a single-threaded determinant to describe that.
So you say you can possibly do a Hartree-Fock approximation preliminarily.
Yes.
Build on top of that.
Yeah. So yeah, you can Hartree-Fock. I would say it will lie within a generalized construct, but it lacks correlation. Yeah.
Absolutely.
Yeah.
Okay. You have a statement which I may not understood correctly. At least in the version that I have, it was in section 3.5, and probably is the same in the printed version, but now I have it on a different page. So you describe the GPO software, and then you say that the computational time increases like a cubic power, and to the third power. And you say that to reduce the cost, one can use a grid instead of the fine grid, a coarse grid instead of the fine grid.
Yes.
And to reduce the time.
Yes.
And here I didn't understand actually. Do you? You say you can do a more efficient calculation if you use a coarse grid, but don't you lose information? So now what you
Yeah. So
don't you incorporate extra errors? And how is the control of errors? Because you don't do n to the third.
yes.
Then you do less, but maybe. Can you comment on this
Yes, of course.
statement?
So, yeah, we say here that it scales as n cube, and this is just because we need to diagonalize the matrix. In practical calculations, it will be maybe n to the power 2 point something. But regarding fine and coarse grid, is that so this is applied for estimation of orbital density dependent terms. And then we need to estimate these terms many times, right? And then if we will use a fine grid, of course, it's expensive, and I wanted to reduce computational time. It will not reduce the power, it will n to the cube, it still scales the same. I just wanted to reduce the pre-exponential factor in the calculations. Now, one of the way of doing that was, instead of estimating orbital densities on a fine grid, which I use in GPO, we can use a coarse grid, which I always use to represent wave functions. So, and use this grid to describe the orbital densities too. And of course the question is, we win and spin, but what's about accuracy? And then, so I calculated the atomization energies of molecules in figure 3.2. So I'm sorry, but probably this is not very clear. Here there are two lines. Red line is when I use a fine grid, and the blue line when I use a coarse grid. And I can see that calculations gives practically the same result. So this is verification of the fact. So this is just verification that I can use a coarse grid for estimating this term. So yeah, we basically, of course, when we do some approximations, like reduce grid size or something, we always need to be sure that we don't lose accuracy too much. And I verify that for these, at least, systems, we don't lose it. But of course, in practice, we always need to be sure that we converge results with respect to basis set size and grid and yeah, everything. Yeah.
Okay, how about the self-interaction?
Yeah.
So, how bad is to
do
ignore it, or how bad is to allow the self-interaction? You showed an example, and it's very nice that you say in this system, you basically include the self-interaction corrections and all of a sudden some bound states become delocalized or something, yes?
Yeah.
What is the
Yeah.
meaning of negative energies and positive energies
Yeah.
in this case? So
Yeah, so, yeah, here,
bound versus free states.
yeah, so this state is just not practically not bound as compared to energies of
But
atoms.
isn't this something that you need to take care in a small system? What if I have a lot of electrons? Do I have to care about that?
So I cannot answer this question in advance because it depends on the system, and then so we should not be worried to apply this method to calculation of other systems with many more electrons, because this is the purpose of this first principle calculations, that we develop this method and we will apply it to all different kinds of systems and see how it works. Yeah.
So Hartree-Fock approximation has this problem.
So yeah, Hartree-Fock actually, yes, I think it will be. It will. So Hartree-Fock, I think it will not have this problem with a PB, like a PBE has. So I think the state actually will be excited state with Hartree-Fock.
I mean, fundamentally speaking, why not? Because what is self-interaction? Is actually you write at least the Hartree term based on the density,
Yes.
right?
Yes.
If I have one electron, I still have that there.
Yes.
And that's a principle. You need to,
need to
exclude the spurious
Yes. Self-interaction.
interaction of an electron with itself when you transform the particles in density.
Yeah.
Yeah, that's the idea. So
Yes,
that's
of
what-
self-interaction correction. Yes,
So
exactly.
basically, if I have many electrons, maybe
Yeah. So in many electron
maybe it doesn't
region.
matter.
So you think that self-interaction error reduces in many electron systems?
I tend to believe that.
Okay.
Because basically you say, what about having one electron extra or not? Because that is, but you tell me.
So in many electron system, so first there are actually different definitions of what is self-interaction error in many electron system. So what we use here, we use single orbital, like one electron self-interaction. So we know that in one electron limit there is a self-interaction error, and then I have many electron system. Then the total self-interaction error is just sum of each self-interaction errors.
Something.
Yeah, and this is of course approximation. And then the question is, it's a good question. What is true self-interaction error in the many electron system? Right now we just approximate it as a sum of single electron errors, but it's actually what we can see is that because we need to scale the self-interaction to the many electron region, probably this approximation is not good enough. And in the future work, one need to develop a better form of a self-interaction error for many electron systems. So, I'm not saying that this is ultimate theory. So I think we should work on that more and develop a different form of the self-interaction error in many electron systems. Yeah. So I can just say that if you have a very localized electrons, and then you can distinguish the electrons from, of course, if you have metallic system, there is no orbital there, it's just density and what is
That's
single
the
particle
origin
test.
of the DFT theory.
Yes, but if you have localized states and they are separated, then I think you can define the self-interaction error, in this case even for solids.
So you say for localized electrons, the self-interaction error is
Important.
important.
Yeah,
The self-interaction correction is also
is important. And for delocalized, you just can use, for metallic systems, you can use LDA, PVE, and it works fine. Because, electron delocalized and orbitals are not so well defined there. And I think this is indication that, maybe self-interaction error. I should say self-interaction error is there, but approximation to the exchange functional is so good that it practically cancels. So yeah, for delocalized states.
Okay, so maybe one final question. Tell me 3 novel elements in your work that you are proud of.
Well, I'm proud of.
Yes. Number 1.
I'm very
number
modest,
3.
I should say.
So,
Well, I generally, I like that we develop a method which is finally can allow us to perform calculations without thinking too much about technical issues. For example, if you do calculations with DFT, use some code. If you're lucky, maybe 50% of calculations, your calculations converge. And then you may spend a lot of time on adjusting parameters of density mixing, try to converge calculations just to get results.
So what you're saying is the same probability of being lucky or not?
Well, okay, maybe 50% was too much. Let's say 20%. But now we have a method which is more robust. And finally, when I developed this method, direct minimization with the producing a self-interaction correction, I finally was relaxed when I was doing calculations. I have a good program, I can submit calculations, and I finally can do physics. So I think this technical achievement, it's important. So the second good thing about the work is that we develop methodologies for excited states calculations. And what is good here is that it's, again, robust algorithm, and the fact that we can do excited state calculation at the cost of quantum density functional theory. So it's the same cost as the ground state. This is, I think, this is a positive thing about this method. And then I also I like that we managed to implement it in a solid state codes, so like GPO, because now I'm just excited to see how we're gonna use it and to see how many systems we can simulate. So we can do now excitation as a solid in condensed matter. We can do dynamics in the excited state. It's just open up so many possibilities. And the most important thing is now we can really focus on the development of the self-interaction corrected orbital density dependent functionals. So I think this is really good. Yeah.
Thank you.
Thank you.
So Andrei, thank you for your questions. I hope we still have Thomas on the line somewhere.
Still here?
Yeah. Do you have some additional questions now?
Well, I had a few questions on solids that were covered, but maybe just one. I mean, did you try? There's nothing that hinders you in applying your methodology for excited state to solids, right?
Yeah.
So what would happen if you try to do that? Would it work?
Yeah. So actually, I already tried. So one system we are looking at now is nitrogen vacancy defects in silicon. So you, in diamond. Sorry, nitrogen vacancy defects in diamond, and there you can have localized states, and you can calculate excitation energy there.
Yeah.
So actually, people did calculations for triplet states before. But only lower state. So now we would like to explore it further and calculate higher excited states. And also, I found that people didn't do calculation of singlets because they say this is a strongly correlated system. And but now we want to assess the spin purification formula and to see how this will work for such system. But I already performed calculation for triplet states in this system, and algorithm just works fine and yeah. Works well.
Yeah, but I was also thinking about something like bulk silicon, for example.
Okay. Yeah, so
Have you tried that, or do you think it would work?
in silicon,
Silica, silica.
silica, okay. In silica, yeah. The only thing is that, okay, in this method, you should be sure that the state you excite is not very, it should be kind of localized.
Yes, and why is that? What was the so what would you get if you tried to do it in bulk silicon, for example? What would you get for the excited state energy?
So, yeah, you will get excited state, but because PB, as far as I remember, predicts very small band gaps there, right?
Yes.
It's so you need to smear probably electron. I don't know. It's yeah, it's gonna be a bit tricky because your electron is delocalized. You need to have then very large supercell, I guess.
Yeah.
And it's just practically will be difficult to calculate such a extended.
Why do you need that? I mean, you have K points, right? So you can.
Yeah,
just
you
use-
can do K points. Yeah, for if it's pure silicon, yeah, in principle you can just do K point sampling.
I
so
think
I-
you just get. I think you just get the Kohn-Sham band gap if you try to do it.
Okay, yeah, okay, yeah. I need to check that.
Um, Can you see why that is?
So why you get just a HOMA-LUMA gap?
Yeah.
If you promote an electron and try to do excited state calculations on on that.
Yeah.
Oh, okay, okay.
That's my feeling at least. But,
Okay. Yeah.
so how would the density change?
Yeah, density will not change much actually, because the
No.
gap is small.
In the limit where you, I mean, in the limit where you have very dense K-part sampling,
Yeah,
then the density will, I mean, the density change will be extremely small.
yeah,
You will not change the external potential. You will not change anything. The only thing you get is the Kohn-Sham energy differences,
okay,
I think.
yeah. Okay, yeah, this is actually a good point, yes. So, yeah, I was thinking maybe if we could use some localized orbitals and do excitation into these states, for example, to construct Pipec-Misey or Foster-Boy's one-year functions, and to do excitation into these localized orbitals. And then I think density will change more, and maybe this will allow to describe the excitations.
Yeah,
So
but
to
how
use
do you
localized
relate that?
orbitals. Huh?
How do you relate that to the band gap?
So, but sorry, why do we talk about band gap now?
I'm asking, can you use delta SCF? Can you use delta SCF to calculate the band gap of solids?
So actually, band gap, not really. The
No.
problem with, so band gap actually, this is not a optical excitation, right?
Okay, so let's say an optical excitation, the optical band gap,
Yeah. Oh, okay. Then,
optical gap in a solid.
yeah. Then, yeah. I think, yeah. If we use localized orbitals, yeah, construct localized orbitals in occupied space, and then just promote an electron to localized state. So this should describe, yeah, it's a good question what kind of excitation it will describe, but I think, yeah, it should describe for sure some optical excitation. And then we need to look at the symmetry of the excited state and then to relate it to the experiment. But I think with localized states, we probably can do this.
But the excited state is a delocalized state.
Yeah, so the empty states are delocalized, but I think can't we apply also like localization procedure to the empty states too, and localize them?
Yes, but
So-
then they're not eigenstates anymore, right? Or
They're not.
eigenstates.
Yeah, they're not eigenstates. No. Yes, but then we estimate the excitation energy as just energy difference between ground and excited state, the total energy difference.
but the excited state is delocalized. So you're talking about promoting an electron to a localized.
Yeah, to promote an electron also to the localized states.
But
So-
that won't tell you anything about the excitations, right? That will tell you about.
Yeah, I guess we need to look at the symmetry, final symmetry. If they, but localized orbitals, yeah, they might have problem. Yeah, usually localized orbitals doesn't have symmetry of a cell, right? But yeah, this is a good question. But I think at least in system where there are separate levels, like defect states, there for sure we can calculate
Yeah,
excitations.
if you have localized states,
Yes.
then you can do it. But
Yeah.
not. I don't think it will work otherwise.
Yeah,
Unless you have an orbital-dependent functional, that might
yeah,
give you something. And that you actually have when you have the SIG. I mean, that's
Yes.
orbital-dependent.
yes. Yeah, this actually can help. But I think the most important thing is just to open up the gap, really, and to localize orbitals. As soon as a gap is opened, it's a finite, and it's not small. I think in this case, it shouldn't be a problem to describe the excitation.
I don't know, but that's what I'm talking about. Bulk silicon, that's a finite band gap.
Yeah, but with the PB, it's extremely small, no? It's like practically zero, like 0.2.
Okay, let's take another example. Sodium chloride.
Yeah.
It's the same problem.
Okay. Yeah.
I cannot see that it's possible.
Mm-hmm.
Would you think it?
I would like to try that. I would like to try to do this now.
But I think actually that SIG might help a little bit because it's orbital dependent.
Yes.
And that's so you get something else than just the Cohen-Sham gap. And I don't know. I mean, you can do it in exact exchange and maybe RPA. You could do something.
Yeah.
I don't know. But I think it's tricky.
Okay, yeah. I can see it. Yeah.
But I just think that you need, in that case, you really need information about the excited state in the functional. Otherwise, it's, yeah, I don't know.
Mm-hmm.
It should be doable in some way, but I'm not sure how.
Okay.
Okay, I don't think I have much more. Maybe a final question in the same spirit as Andrei's. If you had to do your PhD all over again, what would you do different?
Mm-hmm. Yes, it's a good question. So there is the thing that is that we cannot really go around the development algorithm and implementation of them in the software, right? There is no way around of that. So if I were in the beginning of my PhD again, I would do this again, but at much faster speed. And but I would keep my eye open also on more on the development side of the orbital density functional theories, and probably would do more theoretical work there, and focus more on solid state applications. Because I would have more time, right? If I had to implement it again, yes, yeah, right, yeah. Thank you.
Okay, good. Thank you for all your nice answers.
Thank you.
I don't have anything else.
Thanks.
Okay, thank you both again, Andrei and Thomas, for the questioning. Thomas, you're still with us. We now need to, you got two Zoom addresses, I hope?
Yes.
Yeah, so now you're supposed to log into the other one, because then the audience can't hear you anymore, hopefully.
Yes.
And me and Andrei, we will go to another computer in another room, and then we have a short meeting, and then we will come back here.
Yes.
Okay. See you on the other Zoom then. Okay. You can, yeah, relax.
Yeah, I used to, like, it was 20 copies. Yeah.
There are plenty of empty seats there. Did people leave already? No. 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 Was there? I don't think so. There are 3 empty seats. There are 10%.
So here we are again. We have had a small meeting, and I'm just basically going to announce the results. It's not like a 50-50 like we were discussing before, maybe 20-80. But actually, I have to read here, because I'm supposed to read this properly. I normally don't follow a script, but this time I will. So the following has been entered into the PhD examination log of the Faculty of Physical Sciences and signed by me and the faculty opponents. And I will first do this in Icelandic. You just bear with me, and then it will be in English. So, með ályktun Raunvísindadeildar var ritgerð Aleksei Ivanov, Útreikningar á orkulágum og örvuðum rafeindaástöndum með orkufellum leiðréttum fyrir sjálfsvíxlverkun. This was your thesis in Icelandic. Tekin gild til varnar fyrir doktorspróf í efnafræði. Að fenginni álitsgerð dómnefndar samkvæmt háskólalögum. Vörn farið fram í heyranda hljóði og hún tekin gild. Því lýsum við því yfir að Aleksei Ivanov með réttu doktor í efnafræði, filosofía doktor, frá Háskóla Íslands. Þetta sé góð og heilli gjört og vitað. Og now we take it in English, okay? By resolution of the Faculty of Physical Sciences, upon the recommendation of a special committee, according to the laws of the university, the thesis entitled Calculations of Ground and Excited Electronic States using Self-Interaction Corrected Density Functionals by Aleksei Ivanov was accepted for defense for a degree of Doctor of Philosophy in Chemistry. A public defense has been taken place and this has been accepted. We accordingly declare that Aleksei Ivanov is rightly declared PhD Philosophia Doctor in Chemistry from the University of Iceland. So in accordance with this resolution and on behalf of the Faculty of Physical Sciences of the University of Iceland, I will now present to you this doctoral certificate. And we have two copies. This is the nice copy and this is the less nice copy. So congratulations.
Thank you very much.
Thank you.
Thank you.
So I would first like to ask the opponents if they want to say something positive, possibly, to Aleksei at the end. Thomas, maybe you want to start if you're not muted.
No, I have unmuted myself. Well, I just want to say congratulations, and I wish the best for you in the future. You've done a nice work, and I think you'll do good, whatever you decide to do. I don't know, do you have any plans for the near future?
Any plans? Yeah, I would like...
Or stuff like that. Are you continuing research or...?
Yeah, I would like actually to try to stay in academia, at least for the next few years, and find postdoc position, and yeah, closely related to my project now. So, exciting time ahead.
Okay, good.
Yeah.
Well, thank you, and good luck with it.
Thank you.
Congratulations and for your work and for the exciting improvement of the approach of the to the excited states. And in practice, I really would like to have as good as possible method to calculate band gaps, especially at interfaces. For example, we have now some funding for understanding the solar cells based on the perovskite, halide perovskite, and this is a development. So we had a project and we had some extra funding for doing some molecular dynamics and DFT calculations, and I spoke to Hannes and I wanted to increase the connections with your group to do something together. So it's important that this is in your or in the group focus, the solid state.
Thank you. Yeah, it's very exciting.
Thank you.
Thank you.
Then Aleksei, do you want maybe to address the audience?
Yes. If I can. Okay. So first, I would like to thank the professor Einar Örn Sveinbjörnsson for chairing the defense, and I would also like to thank Þuríður for helping to organize this event. Also, a big thanks to my opponents, Associate Professor Thomas Olsen and Professor Andrei Manolescu, for their constructive criticism and for giving their spare time to oppose me. I appreciate it a lot, and it really helped me to critically look at my work from different perspectives. Thank you very much. And now I would like to thank my academic supervisor, Professor Hannes Jonsson, for his work with me, for constant academic guidance, for support, and yeah, I cannot express how lucky I am that I have had this opportunity to work with you. It was really a fantastic time, and I really hope that we can continue our collaboration for the foreseeable future. I also thank to Elvar and Gianluca for their collaboration. It was really great and fun time to work with you. Also, I would like to thank all my colleagues from VR3 and beyond for their useful discussions and giving me feedback during the seminars. Also, special thanks to Dr. Pavel Bessarab and Professor Valery Uzdin, who is not here but is hopefully watching us online, for their frequent advice during my PhD study. And finally, many thanks to my family, my parents, my sister, my wife Sally, who is here, for their support during these years. And thank you everyone here and online for watching my defense. Thank you.
Thank you, Aleksei. I have only two more things to do. One is to give you a present.
Oh,
Yeah.
nice.
Here a bag. And there's one solid state and one liquid state.
Oh, nice. Thank you. Thank you very much.
Congratulations again.
Thank you. Thank you. Thank you.
So I hereby basically close this session, and I thank again Thomas and Andrei and Aleksei and all of you for taking part in this ceremony. Thank you very much.
All right. Okay. Thank you. Thank you. Thank you. Okay.
Okay, bye, Aleksei.
Okay, bye. Thank you very much.
No.
It was good to see you.
See you in the future.
See you in the future. Bye bye.